Yeah, welcome. Good morning. I'm standing here now after about 1.5 years after the last workshop where we discussed how to track rhythms and meters in odd music. So something that is not 4/4, basically. Everything else is odd. Back then we had some discussions and we thought about how to do that, and well, one nice thing that happened is that now standing here again, basically we have one first approach here which achieves that goal. So we did a major step here, I think, with this model which I will present to you, but also other researchers have done important advance, so it's not only this specific model. Okay, let me give you our motivation. So what we want to do is we want to have approaches for music analysis, computational approaches, I should say, which are adaptable. So they can adapt easily and possibly automatically to new musical styles. So the focus of the applications would be then music recommendation and digital distribution on the one hand, and also research in ethnomusicology on the other hand. So this two-folded motivation is at least what drives me in doing that research. So I have the hypothesis that many methods, at least in MIR, in music information retrieval, are tailored to certain styles of music. So this was maybe very much the case, at least until some years ago, in approaches like beat tracking, which aim at estimation of a beat sequence from an audio signal, but also in other analysis tasks that might have been the case, or even might still be the case to some extent. And the question is then, given the diversity in the musics of the world, can Bayesian methods, for example, help to avoid a bias in MIR applications? So a bias which means that we train or we develop our models in certain styles, and they will not work properly for other styles. That includes a bias in whatever software system you would use this kind of analysis software. So I give you a problem definition to be clear here. So what do I mean when I speak about meta inference? So when I speak about meta inference, I refer, first of all, to an audio signal, to a recording of music performance. And given that recording, we would like to determine which type of meter we have in that performance, and we would like to align the layers of this metrical hierarchy, however it is formed. We would align these with the audio signal. Applications are several. I have 3 examples here. For example, music recommendation. Play me some slow pieces, useful, for example, if you want to have an automatic playlist for your romantic dinner. You would like to avoid it throwing in some song by Slayer or Napalm Death randomly. Another application would be music performance and production, where I don't have so much relation to, but surely that is also interesting. And the third application is maybe the most interesting for me personally. So it is basically to determine typical rhythmic patterns in a set of recordings. So doing some kind of a corpus analysis of a set of music recordings. Our research then proposes a unified model to determine meter type, tempo, beats and downbeats from an audio signal, so to do all that in one unified approach. And we propose some efficient inference mechanisms to infer the metrical structure from musical audio signals, because I will not be able to go into much detail, but the inference, so finding out these kind of alignment and meter types from an audio signal using these kind of models which we are using here can be quite demanding, especially if you go to larger music collections. So we need efficient inference mechanism to do so. So far, until now, such an inference could not cope with the ambiguity which arises due to tempo and phase ambiguities in music. So there was a problem using these efficient inference mechanisms so far, and we were able to propose some things which can cope with that now. So now we can, by training our model, we can track arbitrary meters. I should maybe say arbitrary short meters, as for instance a 9/8 aksak. So the model structure. So I struggled a little bit with these slides because in order to be concise, I would need to put a lot of equations in the following slides. Yesterday evening, I just threw them all away. So I will be not concise, but I hope this way I can keep some people who would otherwise get lost a little bit more inside the presentation. So I hope I can manage that. So the basic philosophy here is that we use the bar pointer model. It has been proposed in 2007. Frankly speaking, what does it do? So at the downbeat time, so at the beginning of a metrical cycle, the bar pointer takes a value of 0. Then it continuously increments in steps depending on the tempo. So you can see this, maybe it's not so well to see, but you can see this slope here. This is the bar pointer increasing. So this slope basically depends on the tempo. Then when it reaches a maximum value, depending on the length of the meter which we have, it is reset to 0. So it does this jump back, and then it starts again from the beginning. So the trick now is that this tempo is supposed to be able to change within a bar. So what we need to do is at each analysis time frame, we need to estimate where are we in the meter, at which position in the cycle, which tempo do we have, and what type of meter do we have. It might, in principle, change as well. So, and that looks like this. So I will give a hopefully intuitive example of how that looks like. So that's not music I'm particularly familiar with. I always need some cycles to find it. So. But I think this might have been an intuitive example to visualize what that model actually does. So I will go into some detail now how it does that. So I said that this bar pointer model should have 3 elements. One is where am I in the cycle, how fast am I moving, and what is my meter type. And we put these 3 elements into what we call the bar pointer X. So this is what we want to infer for a given audio signal. Again, I don't discuss now the smaller details. They are there if you want to have a look at the slides later or want to discuss things with me later on. So important is to remember that we have these 3 elements in what we refer to as the bar pointer, in what we want to infer from our observations. Then we assume, in the general form is that we assume observing a sequence of data, Y. Let's say we have K, capital K, number of observations, and we want to infer from these observations our hidden variables X, which is this 3-element bar pointer model which I showed you on the slide before. It is now a practical approach to do a factorization as shown below there, because such a factorization enables us to do that in efficient ways, which is factorization in the form of a hidden Markov model. So we assume that we basically would like to have exactly that thing on the left side. So we would like to know the combined probability of having a certain kind of observations and a certain constellation in our so-called hidden variables. This factorization then has three elements, as you can see. So it is one element, the first one over there, which gives you a kind of the possibility to put some prior knowledge into the system. In our case, it would say, for example, which kind of tempo would you allow from the beginning. And then you have these two important things afterwards, which are once the transition model, which kind of models, which kind of development you would allow, for example, which kind of tempo changes you would allow from one frame to the next one. And you have the so-called observation model, the last thing, which couples the whole model to, let's say, to the real world. So as I said, okay, the initialization, so the first element is pretty simple. We only restrict the tempo range. The transition model, now frankly speaking, that's the place where there were a lot of equations, and I cleaned it up a bit. So we assume that we have one specific underlying rhythmic pattern R in one recording of known length in beats. That's what we assume. That's not necessarily so, but that's what we do in our experimental setup here for now. Then at each analysis frame K, we assume that tempo somehow varies smoothly, following a normal distribution around the previous value. And the current position in a bar is simply derived deterministically from the previous position plus plus an increment which follows from the estimated tempo. That's all. The observation model then, so that what links our model to the reality or to what we think is the best version of it, is a feature which describes the positive energy change in spectral bands, what we call in our engineering jargon, which we call spectral flux. Some people propose also using the superflux, which is apparently the best way to do it. Then our observation model then basically says, given the bar position and the type of rhythm, so two elements of X, how likely is the current observation? That is what this thing basically tells to us. And we learn this likelihood function, which we need for that, in an offline way, supervised on annotated data. So we get these kind of rhythmic patterns, which Florian also discussed a little bit yesterday. So they kind of couple our hidden variables to reality. They say, for example, in this form of rhythmical style, it is very likely, for example, to have high energy changes at certain instance in the high energy bands and in the low energy bands. So this is our observation model. So now we come to the things which are actually even more nasty to explain. So let me try again now to make it simple. So imagine we have these this bar pointer, which has, as I said, these three elements of where am I in a rhythmic cycle, the tempo, and the type of meter. Let's simplify and do it only regarding the tempo and the position in the bar. This, okay, we should assume that this is a continuous space, basically. So tempo values could take on basically all kinds of values, and so the position in a bar. But in order to do an exact inference in that model, we need to discretize that space. The problem is that only for a very fine grid that works nicely. But if we do that on a very fine grid, the needs for memory and the computation times get extraordinarily nasty. So what to do? Don't be afraid. What we need to do is an approximate inference. We need to do an approximate inference. We need we don't do that discretization of this space, but we use something which is referred to as particle filters, PF. So without now explaining you algorithms, I will just show you an example and try to explain it visually. Okay. So what is that what we see here? First of all, ignore that thing down there, the smaller plot. We have a look at this gray and white figure up here. Let me just skip a little bit into. So what we see here, the background, the gray and what? 5 minutes? Oof. The gray and white thing on the background basically describes what we would like to achieve. And these colored things are basically our particles. And what we would like to achieve is that these dots cover the whole area equally, and especially the bright areas, which are the areas which are high probability areas in our state space. And this blue dot is very important because that is what we like so much to refer to as the ground truth. So you see something here. All the particles went away from the ground truth. That's bad. We cannot do it with, for example, this very simple inference algorithm. But in our paper, we then developed a method which can actually cope with that. And then it looks like this. So basically, you can see now that all these particles are flying around nicely in the space on high probability areas, and they always cover our ground truth. So that means that this approximate inference enables us to achieve a similar performance with much less computational means, and that is the first time that such approaches are now applied to music signals with success. So I just run through that. So we have 2 papers together with Florian, with my supervisor in Istanbul, Taylan Cemgil, with Florian's supervisor Gerhard, and the other paper also together with RJ. So we did some tests on culturally diverse data. Basically what we have here is Cretan music, Turkish music, and Carnatic music. And we assume in one experiment that we know the rhythmic class and want to determine beat and downbeat. And do a second experiment in which we just do the whole thing where we also want to infer what type of meter we have. So in our results show that we can do that. Here are only 2 examples for one Indian Carnatic cycle and for the Turkish cycle. We can, knowing the cycle, knowing the type of meter, we can do that extremely well. And even if we have to infer the type of meter, we still have a performance which is far beyond what has been reached so far in beat tracking and downbeat detection approaches so far. Again, I don't want to imply that this is the only model that can achieve that. Also, others have now in parallel achieved very nice advances here. So I will skip through that. It basically only shows that our model is able to differentiate between the rhythmic styles as well very nicely. And I just want to maybe conclude with one final experiment which I did on Cretan music then, as ethnomusicologists motivated to find out something about Cretan dances. I found that 2 accent patterns represent the majority of the accounted accent patterns in the dances I'm looking at. And these patterns are these 2. One which emphasizes a lot the downbeat, and another one which does not do so. And you can see on the right that there are several dances, and some of them make a stronger use of this downbeat pattern, which is the black bar, And some of them make more use of this less strong downbeat emphasized pattern. For example, the fourth one, Susta, has a higher white bar. And that's a very nice result, because that's actually something which came out of interviews with local musicians over there, who said that this dance is more, the Susta is more even and a little bit like it has more elegant jumps, while the other dance, which strongly emphasizes the downbeat, musicians told me, okay, these people in that village, they just, on the downbeat, they just need that. And that's also how the dance goes. But I will play it to you, so the difference is not so obvious. This is the Anoia Nos with a strong downbeat. Now the Susta, the not so strong downbeat. So these are downbeats. So it's not so obvious, just from listening to some of the files. So it's there at that point, a statistical analysis of some corpus showed some interesting results and some interesting correlations with what musicians actually say. Okay, just my last slide, the conclusions. So we saw that that the model is basically highly accurate, and that we can at the same time propose approximate inference mechanisms that come very close to the exact inference. We can track the meter on very diverse data, and we can learn parameters automatically, and we determine meter, tempo, and all these things in one unified model. So the next steps which we are going to do now is node-to-node alignment and going towards a more unified approach towards music, not only tracking the meter, but also taking the other components into account in that model. Explore rhythmic styles. So the model analysis gives rich insight into performance aspects. That's something I'm interested in, but also, for example, RJ is working a lot of that on Indian music. And the cooperation with other fields, ethnomusicology and music cognition. I think that these kind of models, which can in a graphical form be shown very nicely, can enable for a communication between engineering and other fields. And we can also discover musical concepts possibly in various cultures using these approaches, hopefully. So these are my references and my short political message regarding that I hope to be able to listen to Kurdish music without being shot in the next future. Thank you.
Thank you so much, Andre. Questions for Andre?
Hi, thanks, Andre. Just a small question, but the question of the length of the metrical unit. You put the disclaimer in. We can do small units, but how small is small? And is that something that is predefined or just something that emerges from the model?
It's basically just an observation from our experiments. We had in the Indian data, we had the Aditala. So, and there usually the metrical cycles go beyond, I have to look at RJ, maybe easily 6, 7. So we are there, and that's interestingly also what we have from music perception as something like the window which we have for our rhythmic present, let's say the 5 or 6 second. So it is somewhere beyond that. We need other mechanisms, and it seems to be even nicely correlated to what we need. And but that might be coincidence, but that's about the border.
I not quite sure. I got a little lost when you had the multiple point clouds following your ground truth,
Yeah.
one of which followed your ground truth. What was going on there?
Well, when there were certain, there were these several differently colored clouds following.
Right.
So that's basically the approach is that in the basic particle filtering, you just sample from one certain distribution sequentially. And the problem is that you usually get trapped on one particular mode in your space. So everything sticks to that. What we do is then we basically cluster the space, and we have the particle filtering happening in several clusters which cover the space. And these clusters were related to the colors. So it's basically a clustered particle filtering.
But then how do you know which one is right?
Well, first of all, I mean, this just runs through, and we have the particle filtering hopefully covering as much of the probability space as possible. And afterwards, we know, though, when arriving at the end of a performance recording, we know which particle achieves which kind of probability values. So that way, for example, we can track it back.
Okay.
But there are other methods which might be smarter and which might be also then applicable, or which are applicable in real time and so on. But this is, I mean, you know to which sequential path one particular particle is related, and this way you can see which would be the most likely path of it throughout its life, let's say.
Okay, thanks.
The music examples that you gave, a lot of them, well, all the ones that you gave seem to start on the one. Did you try anything that started off the one, and how did that?
Well, actually, the Cretan music examples, since they are the one which I annotated most recently, that it's just randomly where they start. But okay, I mean, the cycle is only 2/4, so it's a very shortest possible cycle. The Turkish ones, I don't remember. Surely we did not cut them in a way to start on the one. And also in our model, for example, we could impose a prior which says that we start our metrical cycle on the one, but we don't. So it is just, we leave that completely flat.
Okay, well, more specifically, it seemed to start on a beat versus off a beat. Did you ever look into that? I'm not sure.
I'm not sure. Okay, I see. Well, we did not deliberately do so, but for example, I mean, in Turkish music there are cycles where for sure the beginnings of phrases are often not aligned with the downbeat, such as the MIR aksak, which is the heavier version of the 9/8 aksak. Their melodic phrases often don't start aligned with the downbeat, so that's. But then again, we would have, for example, a model for that kind of metrical cycle, so it might still work then. So it hopefully would, but we didn't check that systematically.
Yeah, but I think you might refer to the whole sequence starts offbeat, and then you just catch it because you go forward and then do the backwards and forwards.
Yeah, I mean, if it's just an issue of how to cut it or where the actual observation sequence starts randomly in the signal, yes. I mean, that should not be any issue. Yeah. Well, I think since it's a thing which considers the whole signal in a non-causal way, that would not cause any problems. If you do a causal processing in real time, of course, you would have a confusion in the beginning, as would many listeners have.
Right.
So.
And obviously we have a very interesting discussion going on, which will need some coffee to be completed. But thank you so much, Andre, once again.